Welcome, this is Mrs. Nearing, and we're going to talk through some of the problems from the equilibrium quiz review. We've got some KSP, we've got some ice chart, variety of things here. So let's start out with a KSP problem here. So first question's asking me to write the chemical equation for the dissolving of magnesium hydroxide. So I'm going to start out with solid magnesium hydroxide. So all these KSP problems will look very similar. Solid ionic compound on the left. It is going to dissolve, and when ionic compounds dissolve, they're going to split apart into ions. So it's going to make the magnesium ion and two hydroxide ions. If you're wondering why water is not included, it's because water is there at the beginning and it is still there at the end. So you can think of water as being like a spectator. It's not something we would include in the net ionic equation here. So I'm going to write the K expression for this process. Whenever we write K expressions, it's always products over reactants, and we leave out solids and liquids. So that eliminates my reactant here. So my K expression is only going to include my products, magnesium ion, and the hydroxide ion. And don't forget that the coefficients become exponents. So the hydroxide is going to be squared. And then we've got this problem right here where it says I'm adding a certain amount of hydroxide and a certain amount of magnesium. Will a precipitate form? So whenever you see a question like this, will a precipitate form, you want to say, this is a question that's basically asking me which way the reaction is going to proceed. If my reaction proceeds to the right, if you look up here at the chemical equation, that means that it's dissolving. If my reaction proceeds to the left, I am forming a solid. That means it precipitates. So if someone asks you to predict which direction a reaction is going to proceed, you want to be aware that, hey, this would be a good time to calculate Q and compare it to K. And the way I calculate Q is the same way I calculate K. I'm just going to take my concentration of magnesium times my concentration of hydroxide squared. I need to be careful here because I'm mixing together two solutions. When they mix together, I'm going to have a new solution that has a combined volume of 200 mils. So to find out my actual molarities of magnesium hydroxide, I need to do a dilution calculation. So originally I've got 0.02 molar hydroxide, and I've got 100 mils of it, and then I'm going to combine it with another 100 mils of something else, so now my total volume is 200 mils. And what's my new molarity going to be? So it's a 1/2 dilution. Okay, so my M2 is going to be 0.01 molar. And this is going to be the same calculation for both my hydroxide as well as my magnesium, because you notice we added equal amounts of each. So I'm going to go back and plug these values into my K expression in order to solve for Q. So this is 0.01 molar, so is this 0.01 molar. This gets squared. You end up with Q being 1 times 10 to the negative 6th. If you compare this to your K value, so Q is 1 times 10 to the negative 6. K is 10 to the negative 11. So it looks like Q is greater than K, which means we have too many products, is one way I think of it. Because remember, this is just a ratio of products to reactants. So we've got too many products. So that means my reaction is going to proceed to the left. It's going to use up products and make reactants. In this reaction, my reactants are the solid. So in the case of a KSP problem, if the reaction proceeds to the left, that means you're forming a precipitate. If it proceeds to the right, it means you're dissolving. So if my reaction proceeds to the left, that means I'm making reactants, which is my precipitate. So the answer is yes, it will precipitate. So if someone asks you to predict the direction in which a reaction will go, they could be asking you to do it theoretically using Le Chatelier's principle, or if they're giving you some numbers, then what you probably need to do is calculate Q and compare it to K. So let's look down here at some ice calculations. So we've got an equilibrium. We want to write a K expression for this equilibrium. Oh, what's going on here? So my K expression, since this is a base, we call it a KB expression, but it's really the same thing as a KC expression. So it's going to be products over reactants. So these are my products. My reactants NH3. I leave out water because it is a liquid. So I leave liquids and solids out of my K expression. Sorry, I have a new laptop that's acting weird. Okay, and then the question is, what is the hydroxide concentration at equilibrium? So I'm going to set up an ice chart. So any equilibrium calculation I'm going to do, I can always set up an ice chart to solve it. Okay, so I'm going to set up my ice chart. I'm going to ignore water because that's left out of my K expression. And I put in here what we know. I know that I have 0.1 molar NH3. And the question is, what's the hydroxide concentration at equilibrium? So it tells me to start out with just 0.1 molar NH3. So I'm assuming there's none of this to begin with. And then some of my reactant's going to get used up. It's going to be turned into products. Notice it's all a 1:1:1 ratio. This is 0.1 minus x. This is x, and this is x. I'm going to plug these into my K expression. So I end up with x times x divided by 0.1 minus x equals 1.8 times 10 to the negative fifth. My K value is sufficiently small where I can assume x is a lot smaller than 0.1, so I can just simplify this to just 0.1. So I'm going to make this assumption that 0.1 minus x is basically just 0.1 because x is small. And the reason why I know this is because the K value is at least 3 orders of magnitude smaller than my original concentration. Okay, so this can simplify into x squared divided by 0.1 equals 1.8 times 10 to the negative fifth. So x squared is 1.8 times 10 to the negative 6. So x is the square root of that. So we do that real quick. So 1.8 e negative fifth. You should end up with 0.0042 molar, and that's my hydroxide concentration. That is equal to x. So there we go. So that's how it solved this type of problem. So let's try one more. We've got an acid one here. So I'm going to write a Ka expression. Again, I'm going to leave out water because water is a liquid, so I leave those out of the K expression. So it'll just be H3O, A minus over HA. And I'm going to set up my ice chart just like I did before. Whoa, ICE. Okay. So my HA starts out at 0.2 molar. I'm going to ignore my water. My H3O, I'm just going to write right underneath it, starts out at 0. And my A minus starts out at 0. So I'm going to use up my HA. I'm going to make product. This is 0.2 minus x. This is x, and this is x. So I end up with x squared divided by 0.2 minus x equals 6.3 times 10 to the negative fifth. Again, my K value is very small. It's at least 3 orders of magnitude smaller than this number right here, the 0.2. So I'm going to assume that 0.2 minus x is just 0.2 because x is so much smaller than 0.2. So we end up with, x being the square root of 6.3 times 10 to the negative fifth times 0.2, which you can plug that in your calculator, and that will give you the concentration of hydrogen ions. Okay, let's do one more just for fun. Let's do this KSP one right here. So we've got another K expression. So notice Ka, Kb, and KSP. They're all just Kc expressions. We leave out liquids and solids. So in this case, I'm leaving out my reactant. So it's just going to be this silver and bromide. And if I set up my ice chart, Ag, Br minus. Initially, when I have just pure water, I've got no ions here. I'm going to form some ions as my silver bromide dissolves. I'm going to end up with this many ions at equilibrium. Go back and plug it into my K expression. K KSP is 5 times 10 to the negative 13, and then equals x times x, so that's x squared. So x is going to be the square root of 5 times 10 to the negative 13. And that's going to be the concentration of silver. So this one was pretty straightforward. These last three examples all had 1-to-1 ratios in the balanced chemical equation. You want to keep an eye out for those mole ratios because they will affect your change row here. So if you look at the next problem, problem number 5, you'll notice it's a 2-to-1 ratio, so you have to be careful with that. All right. Thanks for listening.